This video is an example of a chi-square test of independence or association for two categorical variables. The following table summarizes randomly selected sample data for defendants in burglary cases, plea and outcome. Use alpha equal 0.05 to test the claim that the sentence, either sent to prison or not sent to prison, is independent of the plea, a guilty plea or not guilty plea. So I have a two-way contingency table with two categorical variables. One variable is the plea and one variable is the outcome. And I've got two potential pleas here, guilty or not guilty, and two outcomes, sent to prison or not sent to prison. And in the body of the table are the counts for each cell. In other words, there were 392 guilty pleas that were also sent to prison. I also included the totals. So I have the row totals. So in other words, this 450 represents the sum of 392 plus 58. And then I also have the column totals. So if you want to find the chi-square test statistic by hand, you're going to need these totals. I'm going to be using the TI-84 to find the test statistic in p-value. First, we need to set up the null and the alternative statements. They're always going to be of the form for the null. The statement will be that the two variables are independent versus an alternative statement that the variables are dependent or related. So the claim is that the sentence is independent of the plea. So in this situation, the claim is the null. All right, so writing that out, plea, either guilty or not guilty, is independent of outcome. Okay, so that is the claim. Versus plea and outcome are dependent or somehow associated or related. Now the chi-square test statistic for a test for independence is actually the same in structure as the chi-square test statistic for goodness of fit. In the numerator, we have the sum of the observed counts. Okay, so that would be all of these numbers here, the 392, the 58, and so on, minus the expected counts, and I'll show you how to get those if you want to do those by hand, over the expected. Now to do this by hand, and I'm not going to fully do this by hand, you're going to need expected counts for each cell. Okay, a cell meaning that this box here is the intersection of guilty and sent to prison. Okay, so the formula for it is pretty easy to get the expected values for each cell. However, if you have a reasonably large table, you're not going to want to do all of this by hand. But to find the expected counts for any cell, it's going to be the row total for that particular row times the column total for that particular column, okay, divided by the grand total. Looking at the table, the grand total is going to be the sum of the row totals or the sum of the column totals. So you could think of it as the sum of all of these four elements or cells. Okay, so for example, if I want to get the expected count for, let's do row to column 1. So row to column 1. Okay, if I'm in row 2, I'm in not sent to prison. Column 1 is guilty plea. Here is the observed count. If I want to get the expected count for that particular cell, I need to take the row total for the row it's in, and that's 578, times the column total for the column that it's in. Okay, and that's 956. And then divide by the grand total. Okay, so turning on my calculator, I get a value of 537.52. Okay, so that is the expected count just for this cell. Okay, so you'd have to do them for all of the cells in your contingency table, and then you'd have to take all of those values and input it into this formula and do it for all of them, and then sum them all up. All right, so what I'm going to do, instead of slogging through this whole thing by hand, I'm going to enter in the contingency table into a matrix in my calculator. Okay, you don't put your information in a list for tests for association. You need to put in the observed counts into a matrix. Your matrix button is right above your inverse key. Okay, it's in small print. It says matrix. So it's a second key. And you want to arrow over to edit, and I'll put it in matrix A. You need to tell it the dimensions. The dimensions of a matrix are the number of rows and the number of columns, and the number of rows comes first. Okay, so I've got 2 outcomes for each variable. I've got 2 rows and 2 columns. So this is a 2 by 2 matrix. Okay, so you'll see that it moves your cursor once you define the dimensions into the body of the matrix, and you can just type in the values and press enter after each. Okay, notice at the bottom of your calculator, it tells you what row and what column you're in, and remember the row comes first. So the cursor right now is at row 1, column 2. And last but not least, okay, so I have my 2 by 2 contingency table. I'm going to go ahead and run the test. To do that, you want to go to your stat menu, over to tests, and it's toward the bottom, so you could either scroll down or scroll up. It's not the goodness of fit, it's right above it. The chi-square test is the chi-square test of independence. It needs to know where your observed matrix is, and it defaults to A, and that's why I always put my observed counts in matrix A. And notice I did not put in the expected counts in matrix B. What's really nice about the calculator is that it will generate that expected matrix for you after you run the test. So all you need to do is scroll down to calculate, and then you'll see that the test statistic, that chi-square value, is 42.56. Okay, so if I had plugged in all of these into the formula, I would get 42.56 with a corresponding p-value. Now that's really small. That's 6.87 times 10 to the negative 11th power. Okay, so the p-value is 0.87 times 10 to the negative 11th. So in non-scientific notation, it's going to have 10 leading zeros after the decimal. So I know the decision is to reject the null at all levels of significance. And in terms of the claim is the null in this case. There is sufficient evidence to reject the claim that the plea is independent of outcome. Now, if you wanted to use the critical value method, you would need to get the critical value from the chi-square table, and you're going to need degrees of freedom. The degrees of freedom for the chi-square test of independence is the number of rows minus 1 times the number of columns minus 1. So it's your row variable degrees of freedom times the column variable degrees of freedom. So I had 2 rows, so 2 minus 1 is 1, and I had 2 columns, 2 minus 1 is 1, so I have 1 degree of freedom. Sketching a chi-square distribution. Now with 1 degree of freedom, it's going to look like this. Okay, but all chi-square shapes, it's a family of curves, are going to be skewed right. The larger the degrees of freedom, the less skewed it's going to be. Like the goodness of fit test, this is always an upper tailed test. Shading an upper tail of rejection, putting in my level of significance given in the problem. I have 0.05, and then I need to go to the table. My apologies, I should have had this ready before I started recording. The table I'm using currently is pretty tricky to read. The areas are across the top in the upper table. Degrees of freedom are down the side. So I have 0.05 and 1 degree of freedom. So that critical value is 3.841. So it's pretty obvious that we are well in the rejection region. If our standardized test statistic is 42.56, okay, we're way off in the tail. Okay, we're over here. We're by the edge of the screen. So there is strong evidence to reject the null. Okay, so there's sufficient evidence to actually conclude that the plea and the outcome are somehow related.